Okay, welcome to Tetryonics 2, which is the quantum charged geometry of matter. In this one we'll take you through from the 0-point fields and equilateral geometry right up to the beginnings of quantum electrodynamics, but specifically all matter up to and including the hydrogen atom. With the 0-point field, obviously one of the key points with equilateral geometry is the fact that you can rotate it and it still has a symmetry about which you can rotate. And then with the addition of electric fields and magnetic fields into the 0-point equilateral geometry, we can see that chirality suddenly appears within the charged geometries of energy. Namely, we have an imbalance in the number of plus and minus energy momenta or charged geometries that can be put into any square geometry, giving us net negative and charged electric fields. These fields can obviously be rotated about any degree, but in this case down the bottom right we've rotated them 60 degrees at a time, and each one of them just gives a different orientation. However, the electrical energy flux remains the same. It's always rotating in the same direction, i.e. in the case of positive, it's rotating clockwise. Electrically, as it notes there, a positive 0-point field can always be modelled as a clockwise rotation or EM flux, and a negative is counterclockwise. The application of imaginary energy flux or imagining 0-point fields as short-circuited quantum inductors comes in handy further down as we look at ways of storing energy without radiation, and vast amounts of it at that, and releasing it efficiently, and also explaining properties such as mass within the matter geometries of tetrayonic particles. Interestingly enough, as visaged here on the X and Y axis to the left, the mirror images of equilateral triangles with EM fields are not the same fields. If you mirror image horizontally or vertically a positive charge field with a clockwise rotation of energy, it's quick to see that it becomes in fact a negative charge geometry. And that chirality is what gives us our positive and negative charged matter. It allows us to distinguish between field interactions further on in QED and light itself, how it works, how it is measured. But in short to say, so far as chirality goes in quantum mechanics, the mirror image of 0-point fields and in fact matter itself, they're not identical to each other, because in mirroring the fields or the fascia of the matter, you create a different charge. The entire process is mathematically described with Lorentz transformations, where you view a field or an energy or a matter of a particle from a different perspective or a different coordinate system. Again, just to reiterate mass and matter, all square number energy geometries are equilateral geometries, and they're all formed from bosons. You'll see to the left here that we have the two distinct geometries of bosons, the equilateral triangle itself, which is just the boson quanta, or quantum I should say, and where you have odd numbered quanta, you still have a charged boson geometry being odd numbers, but it has a non-equilateral geometry. Obviously, as you can see from that illustration, you got 1 plus 3 gives you 4. These boson geometries come together. They couple inductively via their magnetic dipoles, via the weak force, to form larger and larger energy densities. In this case, if we were to measure those energy densities per second, we have a measurement of mass. So these geometries of 0-point fields, as they come together in odd numbers, gives us the foundation for not only energy, but also explains mass and electromagnetic induction, along with inertial mass within physics. A lot of the properties currently described in physics can be alternatively described on a geometric basis, as you'll see over time. The normal forms of bosons that are mentioned within the standard model are W bosons and Z bosons. W bosons were developed in order to explain electromagnetic induction and the transfer of electromagnetic charge from one object to another. You'll note, because of the odd number, when you build any odd number of bosons into a energy geometry, into a boson geometry, you create either a positive or a negative charge by virtue of there always being more positive or more negative in that geometry. The Z boson came about because, for symmetry reasons, it was felt that if there were positive and negative W bosons, there should be a neutral form of the same thing, i.e. a Z boson. In reality, the neutral boson geometry is an even-numbered geometry. If you look closely at those zero bosons, the plus and minuses, you'll see that they're a different geometry to photons, which are inductively coupled along their magnetic bases. In this case, bosons couple along their electric sides. So the geometry is like a half wavelength geometry of a photon. Same energy, same frequency, completely different geometry. So even neutral bosons can be described and portrayed geometrically as a completely different EM waveform to that of a photon. The interesting thing is, when you get odd numbered bosons above number 1, for example number 3 there, when they do couple together via the weak force, as shown, to form a larger energy or neutral energy state, they will in fact create 2 photons out of those 6, and you'll also have 2 charged photons as well. So in a normal electromagnetic induction, what you'd see is 2 photons of energy being exchanged, and a build-up, or it wouldn't even be a build-up of charge, there'd be charge exchanged as well, but more capacitively than radiatively. Right? The bosons, as in odd-numbered geometry, store energy and release it as charge. Photons store it electromagnetically and release it normally as heat or other higher frequency EM radiation. Again, reiterating what the boson EM field is, it's simply a odd n number pi number of energy geometries. They all come together. Again, the energy within each triangle is always a square number, but these numbers can form together to form differing number energy geometries. The minus W boson is a negative charge carrier. A positive W boson is a positive charge character. Energy-wise, they're identical to photons, except for the odd versus even aspect, and their geometries. The bosons, because they are side-to-side equilateral bindings, tend to be half wavelength geometries. If you were to build a photon using the same size fields, they would in fact be a full wavelength. Bosons are, as I've said before, positive charge carriers. They're the ones that are responsible for the creation of charge geometries as they come together. You'll see there that odd numbers, again, as we've mentioned previously in an equilateral energy discussion, odd numbered bosons come together to form square number energy fields, and each odd numbered boson in those fields is a quantum level. It's the transition or the release of these odd numbered bosons that facilitates electromagnetic induction. In fact, when you separate any energy field, i.e. in a generator, into its 2 distinct energy fields, the positive and negative charge as illustrated here, what you're doing is changing a neutral energy state into a charged energy state. And as discussed with the second law of Tetryonics, once you've separated these charges, the first thing they want to do is seek equilibrium. So you now have a position of separated charges, creating a desire to return back to a neutral state. So if you put those charges into a circuit or connect them with a wire, energy will flow until they reach zero again. These bosons will always come together with positive and negative charges, although in the boson form itself, due to Lorentz transformations or looking from opposite directions, you can't detect these charges. They still remain, and the energy fields will still interact via the weak force or the magnetic dipoles to form larger and larger energy or charge geometries. Again, each charge geometry, as shown on the right hand side, will always be an equilateral geometry, and it's these scalar charge geometries that form the net geometry of matter. Tetrayonic theory itself derives its name from the word tetrahedron or tetrahedra, mainly because all matter is formed from tetrahedral standing wave energy. The energy in the tetrahedral geometry circulates in a standing wave form, and it's the tetrahedral geometry that gives the three-dimensional properties and the solidity to matter as we know it. The solidity of matter is not due to the repulsion of electrons as commonly postulated in physics, both QED and relativity. It is in fact a physical property resulting from the physical three-dimensional geometry of tetrahedrons as they come together. So as all matter has a tetrahedral quanta or quantum, the name of the theory itself is derived from tetryons, or the quantum of matter. Again, each fascia of tetryons is purely equilateral energy or mass when measured in a unit of time. When four quanta come together via their weak force induction, they can form a flat two-dimensional energy field with 4 pi, or a 1 pi energy field that's got 4 pi quanta of EM fields in it. These fields can either remain flat and spread out as radiant energy or heat, or with interaction they can actually come together and form a tetrahedral structure, in which case the energy ceases to radiate at the speed of light, but in fact begins to circulate within that standing wave, within that tetrahedral geometry, as a standing wave, with electrical energy going to a magnetic apex and magnetic fields circulating back into electric fields within that geometry. The key point with understanding matter is firstly that it is a 4 pi tetrahedral geometry, hence the name for these quantum particles of matter is tetryons, derived again from the tetrahedral geometry. Mass, as opposed to matter, that these tetrahedrons form, mass is purely a measure of the energy content of each fascia that forms these tetrahedral structure. So if you were to envisage the tetrahedron, inside it is completely empty, with all the energy forming the sides of the tetrahedron. That energy, when measured per unit of time, is the mass of matter. Again, a large amount of confusion has occurred over the years where physics and science in general have failed to distinguish between mass and matter. Einstein took some steps towards it by revealing that mass is a form of energy per unit of time, but still lumped mass and matter together in a stress energy tensor or an energy density. Tetryonics now defines mass as two-dimensional flat energy mass as a measurement of that energy per second, and matter as a tetrahedral geometry. The flat Euclidean energy is obviously two-dimensional, even though there is a slight Z component. It's neglected for the basis of Tetryonic theory, whereas tetrahedral structures, by their very nature, take up volume. They're three-dimensional, and they must be measured in cubic meters or some volumetric measurement of space. So you'll often see mass and matter, where you see energy as a equilateral geometry. The moment you see a circle around it that says c squared, even without the circle, such a c squared, such as on this illustration in the middle, you immediately know that the c squared now makes that a measure of matter, of mass, sorry. Get it right? Mass. That same geometry in the middle forms one side of a tetrahedral geometry that then is matter. The tetryons themselves can come together four ways. They can come together as four negative charges, four positive charges, or a mixture of positive and negative. You'll never get one with three of one charge and one of the other, because bosons cannot form with three of the same charge. The weak force will repel between the similar electric charges, and the boson won't form. So again, equilateral geometries are always made up of odd-numbered bosons, 1 followed by 3. So the simplest tetryon that you can form is a 4 pi energy geometry, which, as illustrated in the middle, starts off as two-dimensional or 4 pi mass and becomes 4 pi matter by forming into a three-dimensional tetrahedral structure. In which case, if you were to measure the mass, it would be a c squared, and measuring it as matter, it would be c to the fourth that you measure it with. The Tetryon Genesis, just quickly explained, is straightforward. This is how we turn energy into matter. First interaction is basically your weak interaction, where the magnetic dipoles of each EM field combine in one form or the other. They either give you positive fields, or they'll give you neutral fields. The difference being the difference between electrostatic and magnetostatic fields. In both cases, by combining, they create zero momenta or zero velocity, so the particles actually stop moving around very quickly and come to a state where they can actually start to couple together with others close to them. They're not moving at away from the point at the speed of light. These geometries keep combining with other equilateral quanta around them to form 4 pi mass fields, or mass energy fields, and these then interact via the electric fields to form tetrahedral structures. Interesting to note that of the 4 possible combinations, you'll have 2 charged and 2 neutral, with the neutral ones making up 50% of the possible combinations of matter available, which means neutral particles should outweigh charged particles in the universe 2 to 1. Once these tetrahedrons are formed, matter continues to follow the second law of Tetryonics and will seek to equalize. It does this by interacting via the charged geometries. Remembering again that with the formation of a tetrahedral geometry, the one half of that charged geometry of the equilateral side is contained within matter. So if you have a positive side pointing outwards on the matter geometry, you will have an identical negative geometry on the inside, but we can only detect with our senses the outside geometry. The negative one, so to speak, is banished from our ability to detect, and all we detect is a positive particle. So within a positive tetryon resides 4 pi of negative charge. Within a negative tetryon resides 4 pi of positive charge. These external charges then begin to attract each other to form larger and larger blocks of matter. So Tetryons are the quantum of matter, and they go on to form large-scale matter as we know it in the way of atoms and planets and stars and ourselves. That interaction between the charged fascias is what we describe as the strong force in quantum mechanics. The tetryon themselves, having been described as coming together in square or equilateral geometries, can also come together side by side, or when they collapse, can collapse into the same geometry as you see side by side. That's a lot rarer because they're half wavelength and they're not a natural state for equilateral energy densities to form into. These middle ones are the stylized examples of positive and negative charged tetryons. As we've noted, you can see there stylized that I've indicated the charge on these objects by drawing the charge on the bottom of the tetryon, and then illustrated the three other remaining positive charged fascia that form that tetryon. I was unable to draw three-dimensional drawings very easily on 2D drawings like these, so that's the way we've drawn them. You also have neutral tetryons being formed, and again, same arrangement so far as the geometry, but this time you'll note that there's where you have a positive base, you also have another positive side and two negatives, and this gives you a net neutral charge. Although even though they're neutral, again something that quantum mechanics can't explain, they come together through the interaction of positive and negative charges on the side of these neutral particles. So they will still bind and form larger and larger particles through the law of interaction. And interestingly enough, these neutral tetryons have been given a name in quantum mechanics to explain their purpose, and that name is gluons, as in they glue the nucleus together. Tetryonics obviously has a major departure from standard model quantum mechanics and mathematics in that it describes 4 pi point charges as being tetrahedral, not spherical. In fact, a lot of the math within quantum mechanics relies on the assumption that point particles and small particles are in fact 4 pi geometries. A sphere and a tetrahedron, as it's pointed out there, are both three-dimensional geometries, and they're both 4 pi Gaussian surface curvatures. The math's been well established for a long time to show that there is no difference except for their final volume, and volume as such has no bearing on the mass of an object. The only thing that has a bearing on the mass of an object is the amount of energy in each fascia. In the case of a tetryon, it's the equilateral geometry in each fascia that gives it the mass, not the volume itself. Matter is a measure of the 3D space something takes up. Its mass is a measure of its energy content. It's often mixed up that people imagine something that has more mass as being a larger matter geometry. That's not the case at all. Tetryons will come together via their charged surfaces and bind with the strong force to form a number of geometries, the first of which 12 pi geometries, or 3 tetryons will come together. They come together in such a way as to form what we call quarks and leptons. Historically, these particles are separated and defined as being distinct from each other, with the quarks having 1/3 or 2/3 part elemental charges. If you assign the quantum charges to the charged tetryons and to the neutral gluons or neutral tetryons, you can start bringing them together as shown here to form the quarks that we're familiar with, both the matter and antimatter versions. In this case, the one that's formed first is comprised of 2 charged negative quarks and a neutral gluon. And you begin to see why the gluon is called the gluon. It sits between the two charged particles, and it's their positive charges and the neutral tetryon that allows the particle to come together. In the case of quarks and leptons, as I said, they're 12 pi geometries. In the case of an anti-quark, you have 10 negative charges and 2 positive. So your net charge on the anti-quark is -8, which is negative 2/3 of the elemental charge. Additionally, you can have 2 gluons come together around a charged negative tetryon, which will form what we call down quarks. Again, 12 pi geometry for the quark, and when they come together, you have 4 positive, 8 negatives, giving you a net charge of -4, or negative 1/3 of the elementary charge of an electron. Anti-down quarks are exactly the same as what we've just described, except obviously there's 2 gluons coming together around a positive charge instead of a negative, which gives us a +4 charge instead of a -4 for the down quark, and we have a plus 1/3 elemental charge. The up quark, which is the remaining one to come together out of the 4 possible combinations, is obviously 2 positive charge tetryons coming together with a gluon in between it, or a neutral tetryon. This 12 pi geometry has 10 positive charges and 2 negatives, giving us a net charge, quantum charge, of +8, or again positive 2/3 of the elemental charge. This has been long debated over as to why quarks have those charges. Tetryonics now explains the 1/3, 2/3 charges of quarks completely, along with their physical geometry, as illustrated in these last 4 pages. In addition to tetryons coming together to form quarks, they can also interact in a different way, and that is with the law of interaction. Instead of being attracted to each other, the tetryons can be forced apart. They're still held together through the weak force along their magnetic dipoles. In this case, in the case of leptons, the negative charges repel the tetryons apart into a stable geometry, and the 3 tetryons are held together by a central axis where 3 magnetic dipoles are held together with the weak force. It's often said that leptons don't experience the strong force. In fact, what's now shown is that leptons do experience the strong force, but they experience it repulsively as opposed to attractively in quarks. So you can see the geometry of electrons is 3 negative tetryons coming together to form a -12 charge, which is equal to the electron's 1 elemental charge. There can also be 3 positives coming together to form a positron with a +12 charge, the opposite of the electrons, or the 2 types of gluons or neutral tetryons can come together to form 2 distinct forms of neutrinos, one being the antimatter equivalent of the other, one being pushed apart by positive charges, the other one being held apart by negative charges. The energy of electrons in motion, and this applies to all matter, but in this case we're highlighting electrons in motion, creates an additional chem field or kinetic EM field, where we have a kinetic energy plus the magnetic moment, all being created by one field geometry, a chem field. These fields that are formed are additional to the energy or the mass energy of matter geometries, and are the result of motion or charged particles, any charged particles in motion. They follow exactly the same square energy geometries of an ordinary energy field. That is E equals mv squared, in this case the M being matter, or the mass energy of the matter geometry in motion. Additionally, it probably may pay to point out that both, in case it wasn't noted, that quarks and leptons are all 12 pi geometries. So their different names only arise from the fact they have different geometries and different interactions. But they are all in fact the same class of particle, 12 pi Tetryonic geometries. Moving back to the chem field geometries, you'll note here that we've got electrons and positrons, or the antimatter equivalents of electrons, drawn here. The matter itself of the particle is velocity invariant, but when the particle itself moves with any velocity, it creates a secondary chem field, which is an equilateral energy field just like any other. This entire system could be represented, as we've drawn at the top of these diagrams in the boxes, as a spherical charge surrounded by a kinetic energy, a chem field with kinetic energy at the top in the direction of its motion, and a north-south or south-north magnetic moment as determined by the charge geometry of the particle in motion. You can apply all these chem field models to particles in motion, be they electrons, positrons, atoms, protons, neutrons, the whole lot. All matter is a charged geometry in motion. They all generate kinetic energy through their motion along with a magnetic moment. They can all be modelled using these stylized chem field models illustrated in the middle. And these models can again be used to indicate the magnetic interaction between particles of different charges moving in different directions. Fermionic matter, or in this case specifically all the 12 pi geometry particles that can come together, all generate chem fields as they are accelerated or move through external EM fields. That quickly shows that in the case of any particle in motion, while its mass matter remains invariant, the energy, the mass energy of its chem field changes with the velocity of the particle. This quickly gives an explanation for the three generations of particles in quantum mechanics. Using our 12 pi, the possible 12 pi geometries of leptons and quarks, we can quickly see that up-down quarks become charmed strange quarks through the addition of more energy in their chem fields. And additionally, those particles, the strange charmed quarks, can become top and bottom quarks through the addition of even more energy in their chem fields, or more velocity. These are the conditions that occur in particle accelerators, where matter is thrown together at high energy and high velocity, creates a soup of energy, which then creates new particles as they form the process we've just previously described, and absorb some of that energy into their chem fields to move off in different directions. So the mass matter of a top quark is exactly the same as the mass matter of an up quark. The difference in total mass is the mass energy that's stored in the chem field once it's created, and obviously that's reflected again by how fast this particle will move once it's been created within the particle accelerator. Quarks themselves are still all part elementary charges. They're all fractions of 12, plus or minus 12, or neutral. So they still seek equilibrium under the second law of Tetryonics. In doing so, quarks will then combine with other quarks to form the next class of matter, and that's a baryon: protons, neutrons, and antiprotons. The baryons are all 36 pi, or 3 quark geometries. The 3 quarks come together again through the strong force of their oppositely charged geometries, their fascia. The plus and minuses bind via the strong attractive force, and this long 9 tetryon geometry that's illustrated at the top will in fact close together to form a more compact geometry as shown at the bottom there. In the case of a proton, it still has 36 pi external geometries, but the compact form expresses a plus 12 charge because of the 24 positive charges and the 12 negative charges of the constituent quarks within that geometry. Looking at them from the top and bottom, as illustrated in this model, you'll see that again they have differing geometries. The best way to fully comprehend the geometries and how these particles come together is to go to the shared geometry, the shared G drive, or to Pirate Bay and download Tetryon templates. Cut out the actual geometries of these tetryons and build all these particles for yourself physically. You'll then see how they come together, how the opposite charges come together, how the electric fields interact at certain points. And in fact, what you'll notice here in this particular one for the proton is where the opposite electric charges come together to form the strong force. In fact, the weak force is repelling itself. The norths and the souths are aligned so that they're trying to repel. First thought might be that would stop the interaction coming together. However, the diamond shape of the electric field is stronger than the 2 single pi shapes of the magnetic dipole, and the tetryon come together to form the proton. Once the strong force weakens, the similar charged magnetic dipole, the weak force, because they're similarly charged, then repel, and that's what drives particles apart and what drives atoms apart as they break down. As the strong force weakens, the weak force then takes over, and the magnetic dipoles push the particles apart, giving them motion. We've just discussed the proton. Again, 3 quarks come together, in this case a down, an up and a down, to form a neutron. Of note is the fact that these particles, these quarks, always come together symmetrically. Neutrons are currently described as being up-down downs or down-down ups, and protons are described as being up-up downs, when in fact they never bond in that sequence. They always bond alternating charges. So in the case of a proton, I'll just go back. The proton will always form from an up binding with a down and another up. So it's a UDU formation, whereas the neutron will always form from a DUD configuration. We still have other quarks that come together, obviously, and in the case of anti-down quarks forming with anti-up quarks, we create antineutrons. Identical in all respects to the neutron, they still have 18 negative and 18 positive charges, giving a neutral charge with a 36 pi geometry that is identical to that of a proton. But if we go back where you see the positive charges on that antineutron, the neutron has negative charges expressed on its outside. A clear indication of what I was discussing earlier with neutrons, where the measured charge also has an equal charge hidden inside the Tetryonic geometry. Again, antineutrons have positives outside. The antineutron geometry externally is almost identical to that of the proton, which is all positive geometries on the outside. The only real difference being the arrangement of the positive and negative charges that make up that charge, and the fact that the net charge is obviously neutral compared to being positive in the case of a proton. And again, of course, obviously you can have anti-ups and anti-downs combining to form antiprotons, which have a negative 12 charge made up from their 12 positive and 24 negatives, the exact opposite of the proton, and very similar to the neutron. All 36 pi geometries, and obviously in the case of protons, exactly the same elementary charge as electrons, i.e. 12. An important point with baryons that's not explained in quantum mechanics and QED at the moment is that the proton and the neutron have exactly the same geometries and exactly the same mass matter. Mass matter is identical in both cases. What is different is the charge that makes them. So one is a mirror image of the other. If you look at that, you can see the line through the center where the reflection is. They are just mirror images of one another. From a matter geometry perspective, the neutron is the mirror image of the proton. Again, reinforcing mass and matter, each charged fascia in the geometry of matter is an equilateral geometry that contains equilateral or square numbers of energy. Those square energy levels or quanta measured per second is what we measure as mass. It's long been assumed that, as I've mentioned before, that if something is heavier or has more mass than another object, it's bigger. In this case, it reinforces what's been taught in relativity. A heavier object simply has more energy per volume or per c to the fourth measurement per spherical geometry coordinate system than an object of less mass. In Tetryonics, we've applied a color code to that again, obviously, to reflect the differing energy levels. So as you see differing color codes on the same particle geometries, you can immediately read into that the energy levels of each fascia have changed, and consequently the mass of the matter geometries has changed within that. Down the right hand side, or actually in the middle first, we have what's called rest matter. These are the particles that have no motion and therefore have no chem fields of their own. They're strictly stationary matter geometries, rest matter. You have neutrons and protons and electrons that combine under the second law of Tetryonics to form nuclei or deuterium atoms. These deuterium atoms, as noted on the extreme right, can obviously have differing energy levels in their fascia, and as each fascia has differing energy levels, the electrons that bind with these deuterium atoms will spin at a different rate. The baryons or the deuterium atoms, the protons, neutrons in these cases, usually have for a 25 squared geometry is an N1, down the bottom is red, a 26N is an N2, and so on up to N to a 32N geometry, which is a level 8. In the case of a 32N energy level or mass for a baryon, when an electron is attracted to and binds with that N8 deuterium atom, it will spin with an energy level of 8 itself. So if you were to build an atom out of differing energy levels, as the electrons bind to different mass matter geometries of nuclei, the electrons themselves will spin at different rates. And it's the motion between one energy level and the other that creates our spectral lines in quantum electrodynamics. As the quarks of different energy levels come together, particularly in particle accelerator experiments where they're put together with more and more velocity, faster speeds, they create a soup of energy and quarks and tetryons. They all have different masses and different energy levels. They break apart upon collision, and within that energy soup, if you like, they recombine through the law of interaction, seeking equilibrium or lower energy states. Once they form, they can form in a whole host of different ways. And this recombining of quarks and tetryons, the tetryons will recombine to form different quarks. The different quarks will then recombine to form baryons and leptons. As all this interaction is going on, we have a virtual soup, and this soup's been known over the years as the particle zoo. The middle illustration simply shows the possible charges that can arise, ranging between -12 and +24 in the baryons that are produced. And the table to the right simply shows you all the possible geometries that can be created out of three quarks at different energy levels, recombining within that the energy of a particle collision. Again, as I said before, with the energy level of baryons affecting the energy levels of electrons that bind with them, we have what's called the hydrogen ionization energies. With hydrogen, which is just a proton with an electron bound to it, a lot of experiments take place in quantum mechanics and electrodynamics where the energy level of the electron is raised up through the addition of energy into its chem fields until the electron either breaks free or is allowed to drop down and release that energy. And in releasing it, it releases it as light or spectral colors. In quantum mechanics, the energy levels have been historically interpreted as circular geometries. In Tetryonics, we show them not to be the case. We show them to be equilateral chem fields associated with each electron. As more energy is added to the chem field, the electron itself spins at a higher rate, indicated by the colors there. And left by itself, you can accelerate or add energy to the chem field of an electron up to energy level 8. And if you stop adding energy, it will drop back down to N1 and release that energy as a spectral color or any other jump in between levels 1 to 8. If you give more energy than the 13.6 electron volts, it will jump to energy level 9, in which case it's no longer bound to the proton and will escape as a free electron with its energy as kinetic energy of motion. Historically, these energy levels have been drawn as circular orbits around a nucleus. No longer is that the case. They're, as I've mentioned, equilateral geometries of chem fields. As drawn at the bottom, the chem fields can rotate one of two directions within a hydrogen when they're bound to a hydrogen atom, to the left or to the right. With the chem fields illustrated by a positive charge with its own nuclear magneton or magnetic moment, north and south, and the magnetic moment generated by electrons moving one direction or the other, or spinning one direction or the other in the nucleus, creates parallel or anti-parallel magnetic moments with respect to the hydrogen's nuclear magnetic moment. This spin up and down is often quoted as being not a real spin. In fact, it is a real spin, and the measured magnetic moments are the dipoles of the chem fields that are created by the motion. The energy levels of hydrogen, as we've mentioned before, go up in equilateral energy steps. The mass matter of hydrogen itself is invariant. Only the energy of its chem field changes. and in doing so it changes the chem fields of electrons that bind with it. These can all be represented through equilateral geometries, and we've done so here. And in this case, to the left, we've got the polar view of the electrons with a color-coded arrow to indicate the direction of spin and the energy level of the chem field. And to the right, we've got the side elevation of the same electrons with color coding again to indicate the direction and orientation of and energy levels of the chem fields of their motion. It's the frequency it's the number of quanta inside the chem field that becomes the frequency of light when it's emitted in transitions between the different energy levels. With the four nuclear forces at the quantum level, they're described within Tetryonics as follows. We have electromagnetic fields, which are just positive and negative charged energy geometries or 0-point fields. The electromagnetic fields form the geometry of all energy, and the measurement of those geometries per second or per c² is the measurement of the mass. They can interact in a number of ways to form electrostatic and magnetostatic energy fields, but in both cases they still contain electric and magnetic forces within their quantum geometries. The weak force, as we've discussed in particles, is the inductive force or inductive coupling force between magnetic dipoles in electromagnetic energy. In the case of energy, they're the base of each equilateral triangle of energy, be it quantum or be it large-scale energy geometries or square energy geometries. In the case of matter, as illustrated in this page, they're the interaction points where magnetic dipoles form. Whether the dipoles are reinforced as strong north-south dipoles or neutralized, as in the case of electrons, they still interact firstly via the inductive edges, which is what we traditionally call the weak force interaction. And because it's a interaction via magnetic dipoles, it's normally termed a electromagnetic induction interaction or induction coupling. The strong force, again, is simply where opposite charged fascia of matter come together through the interaction force to couple together positive with opposite charges to form a strong attraction between the points. It's a fascia attraction of similar or parallel plates, opposite charges, so it's an extremely strong force compared to the edge force of magnetic induction or the weak force. Although historically viewed as an attractive force that holds the particles together, in the case of leptons, it's been shown obviously to be a repulsive force as well that holds the 12 pi geometry of leptons in their distinct geometry, as opposed to that of quarks, where the force is attractive and forms 12 pi geometries of a completely different structure, different matter. This picture just shows the strong force interaction where it forms where the quarks come together to form baryons, and where those baryons again couple to form deuterium nuclei, the quantum of all atomic elements. The driving force that creates all motion and all matter in the universe stems from the equilateral geometry of electromagnetic fields. These two charged equilateral geometries are the foundation of all mass, energy, and matter, and its motion in our universe. In fact, we'll quickly show here how equilateral energy quanta in quantum mechanics is the basis for kinematics or the study of motion within quantum mechanics and within classical physics itself. Equilateral geometries can be quickly put to use to geometrically describe Newton's laws of force. In this case, all square or equilateral geometries of energy are inductive loops of square numbered quanta, and the square root of these quanta, or the square root of energy, is the linear momentum of the system. So equilateral triangles can now be drawn and explained as energy momenta, or representative energy momenta of any system. In fact, you can then draw a circle around these triangles as drawn here and show the mass-velocity relationship of these systems, which is what Newton used for all his force laws. The mass velocity being momenta or linear momentum, and Newton's laws being basically the measure of the rate of change of momentum in a system. Newton focused on the square root energy of equilateral triangles, or the momenta, mass momenta, whereas Leibniz concentrated on the scalar geometries, the equilateral geometry, which is the energy of the system. The charged energy that radiates from any source point or from any particle in motion is an equilateral charge field comprised of positive and negative energy quanta. These quanta create the law of interaction by moving charged particles or acting on charged particles within those fields, equilateral fields, and inducing motion into those particles in one direction or the other. Where these fields overlap, in this case between an electron and a positron, it creates a diamond-shaped field of interaction, specifically where the electric fields interact in the electric component of the chem fields. These superimposed or superpositioned E fields are the geometry of inverse squared laws. In the case of Coulomb, the diamond shape reveals the strength of the force between two charged objects. In the case of Newton, this same geometry is present between two forms of matter, where the gravitational field exists. It again is an inverse squared geometry, and the diamond geometry represented here of electric fields and gravitational fields is an inverse square geometry. Interestingly enough, the square root of these two superpositioned chem fields is their linear momenta, and it is the force between the two particles that's bringing them together, because the strength of their chem fields is determined by the number of quanta in each field, which in turn affects the acceleration of one particle towards the other. So the linear momentum of the chem fields is actually the vector force arrows used in classical force notation for both gravitational and charge interactions. Tetryonics gives us the mechanical basis for the interaction of charged objects and matter itself by gravity. Applying equilateral geometries again and looking at the energy content within each equilateral triangle, we can quickly see that obviously per second of measurement we end up with units of energy as in kilograms, square meters per second squared, or Planck's quanta squared in the case of quantum mechanics, or in the case of measuring momentum, you can see the various formulations. We can measure it as Planck's constant by frequency, or v squared as I mentioned, mass by velocity squared, or momentum by the velocity of the object. So all these different formulations for force and energy, which have been given the unit joule for energy, are simply differing measurements of the equilateral energy content or energy momenta in Tetryonics. Tetryonics obviously has the square root of energy being linear momenta, and the triangular geometry being angular or quantized angular momenta, which can be drawn as a rotational vector, as in the case of these two drawings here, but in fact is a true equilateral geometry. When it comes to extending the thoughts even further to inertia, we can then look at the fact that equilateral triangles, the energy content of each equilateral triangle is made up of smaller equilateral triangles in one of two directions, up or down, positive or negative, and it's the imbalance of these positive or negative geometries that creates charged geometries. And also, in order to accelerate an object from, or any field, we have to increase the kinetic energy field, the chem field. We do that by adding energy or equilateral energy quanta to that field. These fields obviously will resist having additional fields added to them, and they'll also require these fields to be added in odd-numbered geometry or bosons, so that we continue to have squared-numbered geometries with each change. This can be explained traditionally as inertial mass, or you can explain it electrically as an inductive loop that's been short-circuited that resists change to its energy state. But in both cases, it's simply both cases are simply a reinterpretation of the triangular geometry of energy. So with the energy geometries on the quantum basis now within the equilateral energy geometries, we now have an explanation for inertial mass within quantum mechanics. Linear momentum, which is just the square root of the triangle, the height, if you like, of any energy triangle, can now clearly be shown as the square root. That is a line that points in the direction of the motion, and all the formulas of physics and quantum mechanics and science and relativity can be drawn or can be boiled back down to just the square root or height of an equilateral triangle. If you then want to change it to a mass-velocity relationship, you simply mark the velocity at the top of the triangle and draw a circle around the triangle, indicating that it's no longer an energy momenta measurement, it's now a mass-velocity measurement of the same system. The mass-energy momentum of any system boils down to whether you're measuring the energy, equilateral energy by itself, or whether you're taking a unit measurement per time. If you measure it without any reference to a time measurement, it's the energy momenta. If you take a timed measurement of the same system, you then convert it into a mass velocity or a momentum measurement of the same system, in which cases applying it to the Tetryonic formulas and taking the square root of the Tetryonic math formulas, you quickly see that it again is just the square root of equilateral energy. Kinetic energy has exactly the same properties, and the kinetic energy of field, of course, the chem field, is created with any particle or any matter object that is in motion in space. As it moves, the mass matter of its geometry remains the same. However, the energy of motion is put into the chem field, and it is that field that is subject to Lorentz transformations and contractions. The kinetic energy of motion, which is normally expressed as a half mv squared, is shown to be the electric field component of the chem field. It is half the field. The other half of the chem field is, again, as we've discussed, the magnetic moment of the object in motion. We'll come back to this in discussions on special relativity, where we show that it is this geometry that undermines special relativity and provides a whole new foundation where special relativity is no longer required in its explanation of magnetic moments of charged particles, and in fact Lorentz or relativistic contractions of energy itself. The kinetic energy of motion, as drawn here, as we've mentioned, is made up of a matter component and then a chem field, which follows an equilateral geometry and is comprised of kinetic energy and a magnetic moment, all of which the strength of the chem field is determined and proportional to the velocity of the particle in motion. The velocity energy squared relationship of chem fields is determined by the equilateral geometry of the fields themselves. A positive particle, as illustrated in this case on the right, will generate a positive charge chem field, although the charge itself won't be detected as positive due to Lorentz transformations. It will be measured as a neutral kinetic energy plus a magnetic moment of a specific dipole orientation that matches the positive charge arrangement, and likewise a negative charge moving in the same direction is exactly the same but with a reversed magnetic dipole. That arrangement explains a lot of the difficult left and right hand rules of induction and electric and magnetic fields that have developed over the centuries since electric and magnetic fields were first devised and measured. In this page here, we're going into the strict definition of momenta in quantum mechanics. Tetryonics reveals that quantized angular momentum is in fact the geometry of equilateral energy. It's the golden shape of charge, or the golden geometry of quantum mechanics. And when you measure the quantized angular momentum per c squared, you in fact get charge. So the two things are strictly related to each other geometrically. Quantized angular momentum is not a rotation about a point, as is often discussed in physics textbooks. That rotation about a point can be viewed as an electrical property of its ideal inductive loop geometry, but there is no physical rotation. It is an exact relationship resulting from equilateral square triangular geometries of energy. The linear momentum in quantum mechanics can now be drawn and described geometrically as the square root of energy, exactly as it's formulated in math, but can be easily drawn as the vector arrow that reflects the square root of equilateral energy triangles. So in this case, in Tetryonics, we do a V at the top of the energy triangle. We then draw an arrow at the square root, and if we measure energy, we would have square energy quanta with momenta along the center of the central apex of the equilateral triangle, pointing in the vector direction, and it will all be proportional to whatever velocity the particle is moving at. Quantum angular momentum now has to be defined as something completely different to what it's normally described. We have quantized angular momentum, the geometry of energy in quantum mechanics, and quantum angular momentum is now back to the more traditional view of a rotation about a point. In this case, it may be a particle circulating in a magnetic field. It may be an atom rotating on its axis, or a planet spinning about its star. But in this case, quantum angular momentum, with its own distinct symbol, is a physical rotation about a point, as it's always been described. Quantized angular momentum is distinguished with the symbol capital A, or alpha. This comes from a number of reasons, but it will be shown in later sections that the alpha of quantized angular momentum is in fact the hidden fine structure constant, and is the same constant that creates charge and all the coupling constants. So the choice of capital A, or alpha, for quantized angular momentum is more than appropriate in this case. In fact, Planck can be revealed to be just mass quantized angular momentum. Kinetic energy versus momentum In this case, using Tetryonic geometry, we can show that linear momentum is simply the square root of energy, as noted on the right-hand side there, with energy itself being mass velocity squared, drawn with the energy triangle in the center, with square energy levels. So the square root of the square energy level triangle is simply the highlighted height of triangles down the center of the triangle, the straight line, the vector direction in which it is moving. In the case of kinetic energy, which is sometimes mixed up with momentum, linear momentum, the kinetic energy is half of the energy, or mv squared, of the kinetic energy field. So therefore it's the diamond area that points in the same direction as the linear momentum. So Tetryonics shows us not only square energy levels and how they're combined with odd-numbered bosons, but it can also geometrically show us, in a visual sense, the difference between linear momentum and kinetic energy, something that a lot of people struggle with in defining the difference between the two and distinguishing along with mass and matter. Mass energy momenta, again, historically drawn as a right-angle triangle, can now be completely redrawn in terms of equilateral energy geometries, where the quantized energy momenta forming the larger total energy momenta, or mass momenta, mass velocity, can be redrawn as equilateral geometries. These geometries can be applied to everything in physics and quantum mechanics, from Newton's force laws to kinetic energy to linear momentum, angular momentum, mass, energy itself, energy momenta, mass velocity, and in fact even the Lorentz velocity factors, as noted on the right hand side there, can be applied directly through the geometry of what we've got here. As more energy is added to this total energy of the field, the wavelength, or the size of each equilateral triangle in that field, decreases in line with the Lorentz contraction. So again, reinforcing that relativity will say that matter contracts as velocity increases, when in fact it's purely the wavelength of its kinetic energy field that contracts, or its mass of its kinetic energy field that contracts as the velocity increases. The mass matter of the object is velocity invariant. The final note from that page is the bottom right one of E squared is the energy content of a superposition field. When two kinetic energy fields or two electric fields of the equilateral geometry are superposition between two particles or two objects of mass in motion, their superposition fields, the energy quanta in the superposition field, as you can see there is the small pink arrows, their momenta interact, they either repose or they work constructively. They create our lines of force, our force interaction of Coulomb's law or gravitation. So again, the diamond-shaped fields, which are inverse, reflective of inverse geometry, inverse squared geometries, are shown to be the basis of physical constants in this case, resulting from energy or equilateral energy in fields. This one goes into the Lorentz factor of relativity. Lorentz's formulations were the formulations that Einstein based relativity on. He applied them into his relativistic contractions of matter, or specifically of mass energy, as it accelerates, in order to develop length contractions and things like that. The error that Einstein made was not differentiating between mass itself, which is velocity invariant, and matter, and specifically the matter of the kinetic energy field. As is highlighted here, each field, whether it's on the left-hand side, you can see the field at the top. At the top of the field, all fields have momenta, energy and momenta. Their velocity can vary anywhere between v and c, or even higher, but in this case we'll stay with v and c for Lorentz. So as you add more energy to that geometry on the left, the wavelength, or the length of each momenta, all the small ones, will contract. It will become smaller and smaller, and that is wavelength contraction as defined with the Lorentz factor. And that's what the formulas at the bottom along the side there are saying, apart from the Christoph symbol at the bottom right, which is a symbol for same as gamma, but for superluminal velocities. We'll discuss in other topics how in fact the speed of light in a vacuum is not the limiting factor for particles. Work, force and energy. There's a simple relationship between energy and the force you can exert in order to do work. This can all be expressed with equilateral energy geometries, and in a nutshell, the more energy quanta you put into the same equilateral energy geometry, the more energy momenta you have, therefore the more work or the more force you can exert on an object in order to do more work. The energy momentum geometry of mass and matter gives us a number of different features, but they all derive from the square root of energy. Once you know that the square root of any equilateral energy geometry is its height, and it's a vector arrow in the direction of its direction of propagation, you can quickly draw the energy momenta of all EM waveforms, be they photons, bosons, or even standing waveforms such as matter, and even more complex ones such as elements. Using this geometry, you can draw the magnetic and electric fields of every form of energy available in the universe. As we've drawn here, we've drawn the energy momenta in matter on the right hand side and mass on the left hand side. Again, we draw your attention to the fact that mass, or 2D planar energy, radiant energy, is always denoted as a triangle with a circle around it, and it's always written as n pi in the unified field equation. Matter, on the other hand, is drawn as a tetrahedral with two circles or a spherical volume around it, and it's always designated T pi for Tetryonic geometry, which is just a 4 pi geometry. Again, at the top there, you can see the energy momenta relationships between momenta, mass, and energy itself in its various forms, and they're all represented by the geometries drawn there. The particular thing to note here is that electromagnetic mass is a two-dimensional measurement of energy in a unit of time, whereas matter is a three-dimensional measurement of energy. You can mass is a property of matter, but matter as a three-dimensional standing wave cannot be a property of mass. 3 dimensions cannot be put into 2. However, two-dimensional mass forms three-dimensional matter. It's one of the few non-symmetries in quantum mechanics. The unified geometry of energy momenta is exactly as it's drawn there. For any amount of energy, it's always squared numbers. They always increase in odd quantum geometries or quantum levels, and the square root of that energy always follows the Lorentz linear factor, or V on C, whereas the scalar energy content always follows Lorentz's contraction factor squared, or V squared on C squared. One's a measurement of linear momentum. The other formula is a measure of scalar energy. Together they form energy momenta geometries within quantum mechanics. These energy momenta geometries, or equilateral squared numbers, they're charges by virtue of the fact that they are a triangular geometry. They're bosons by virtue of the fact that they are 1 pi geometries. So therefore, when physics describes a Higgs boson, what they're describing is one charged fascia of the many charged fascia that form matter. As you see here on the left-hand, right-hand sides, the left-hand side being normal matter, the right-hand side being antimatter. As the charged bosons come together to form higher and higher energy contents, or mass energy, if you measure in units per second, as they form higher energy densities, they can interact via the weak and strong forces to couple to form tetryons, and again, they interact via the law of interaction, seeking more stable and more equal energy configurations to form quarks and leptons and baryons. So, as energy, as mass is a measure of energy per second, it can now be revealed that the Higgs boson is simply one equal fascia, or one of the fascia of any matter geometry. Its energy content is the mass of matter. So the Higgs boson is the energy geometry that gives mass to all matter. It does this, and it creates inertial mass, because as you try to move the inductive loop of the boson geometry, or the charged fascia, through the vacuum energies, it resists the change of energy that's created. Any inductive loop moving through a energy field, be it electrical or magnetic, will inductively couple and try and increase the energy geometry, the energy content, or its mass. That resistance to changes is inertial mass. It's exactly what Newton was calculating in his 3 laws of motion. It's exactly what Higgs was trying to describe when he formulated the Higgs field and the Higgs boson. The Higgs boson is simply the charged fascia of any matter. The Higgs field is simply the ether that Einstein tried to do away with. The two are proven to be existing. All that's happened is by trying to ignore the ether being there as vacuum energy, or a electromagnetic field through which all standing wave or radiant matter moves, we've had to create different terminology so that scientists would look at it, because once the Michelson-Morley experiment took place, nobody wanted to know about an ether field. In fact, it's necessary in order to create the property of mass within matter. Again, the energy or the mass energy distributions within matter, or the charged geometry of all matter, is simply equilateral geometries, square numbered geometries, with bosons being odd numbers and photons being even numbered quanta within the same geometries. So the nuclear levels, or the energy levels of atoms and of hydrogen when we're testing for spectral lines, are simply square numbers. In the case of bosons and photons, they're a linear or a two-dimensional energy geometry, a flat one, Euclidean. Once you move into tetryons, fermions, leptons, quarks, baryons, they're all T-pi geometries, and the square flat energy levels are found in each charged fascia of the matter. In the case of a baryon, you'll have 36 charged geometry. Each charged geometry will follow the geometry that's shown here, and there will be square number of quanta in each geometry. These energy contents of these charged geometries are the property of mass in the matter geometries, and this energy, or mass energy, is what creates radioactivity, the energy levels of particles that make them radioactive and cause electrons to spin at different rates within the nucleus of elements. Mass-energy relationship is exactly as it was expressed by Einstein. E equals mc squared, with c squared being simply 1 second. So if the circle was to be removed from this geometry that's drawn as mass, it would become an energy geometry. With the c squared circle, it's a mass geometry. And likewise, the square root of that energy geometry is linear momenta. So you can look at it from a energy momentum perspective, or a mass velocity perspective, or again as mass equilateral geometry or angular momentum, which is Planck's constant, and that's the individual quanta that make it up. A lot of those relationships are now just shown to be different reinterpretations of equilateral geometry. The Lorentz contraction, again, linear is V on C, or the square root, the linear momentum of a system. V squared on C squared. The right hand side is just the scalar mass energy of a system. In the case of all energy, you can divide it by C squared to give you mass. Mass energy on C squared is exactly the same as mass by 1 over C squared. They're all different reinterpretations of the same laws, mathematically reconstructed to explain a slightly different facet of the same thing each time, adding to confusion as it went. We can now re-represent all of these properties as a simple equilateral triangle. The scalar energy, or the classical mass velocity arrangements, momentum, can all be drawn in the left hand side triangle. You can see that it's an energy triangle. When measured per c squared, we have a mass measurement, which is again the scalar. The electric and the magnetic fields of the mass or of the energy are scalar features within that. On the right hand side, you can see the distribution of energy within that very same geometry. It's the same energy field. It could have the same energy or same mass if you measure it per second, but the energy that is drawn in this with the additional fields shows you what Planck was measuring when he measured quantum energy or quantum mechanics. In this case, you can see the red, orange, yellow, green, blue, aqua, indigo, violet lines of quantum levels going down the triangle from the top and working from left to right or from right to left. You'll see that there are energy quanta, the first one being 1 quanta, red, 2 quanta being orange, 3 quanta being yellow, onwards till you get to the middle, which is the amplitude of the wave, and then going back down to 1. So they go from 1 to 8, back down to 1. That arrangement of quantum energy produces a natural distribution of energy, or a normal distribution. That's your bell curve that you see throughout quantum mechanics, drawn as a curve to fit a graph, when in fact it's an equilateral geometry. That same distribution of energy gives us wave functions, statistical probability within quantum mechanics and electrodynamics, all those features. And again, the square root of the amplitude is the same thing as the linear momentum, and the square of the momentum, or the square of the amplitude. The square of the momentum is the energy. The square of the amplitude is equal to the probability of finding any one particular energy quanta within that distribution of energy. That's quantum mechanics and the mathematical formulation in a nutshell. We'll hold it there, and we'll do another discussion shortly on the geometry of the constants and how it relates into electrodynamics.